I must say old Danvers keeps the house looking lovely. She certainly learnt that trick of arranging flowers from Rebecca.
I wonder how she likes it now, being ordered about by an ex-chorus girl.
Now, where on earth did you get the idea she's an ex-chorus girl?
He picked her up in the south of France, didn't he?
What if he did?
Well, I mean to say, there you are.
How do you do? I'm Maxim's wife.
How do you do?
If you love listening to this show, please consider giving a rating and a review on Amazon Alexa or wherever you listen. We want to continue bringing you this amazing content, and part of our ability to do that means that we need a big audience. Now, it may not seem like much, but rating and reviewing the show will help more people find us, just like how you found this show. Simply on any podcast platform, search for a show, scroll down to the bottom, and push 5 stars. It's that easy. Thanks for supporting the show. So today I'm joined by Shey Sabripour, who is the founder and CEO of CesiumAstro. Welcome to the show.
It's a pleasure to be with you, Scott.
So you have worked at Lockheed Martin for some 24 years, and of course you've worked on many projects, but one of those projects that you worked on was the Lockheed Martin Commercial Active Phased Array Payload. I wonder if you could elaborate a little bit about that experience.
Yes, it was a great experience. We had an opportunity to launch one of our first commercial active phased arrays on a commercial geostationary satellite, and I was fortunate enough to be able to lead a large team of incredibly smart people, and we had a challenge of getting this built, designed and built, and getting it ready for a demo mission. It was ultimately launched on one of our customers' satellites as a demo receive active phased array, and the program name was called AMC-14, and it was ultimately launched. There was an upper stage failure, and the satellite ended up in a 50 degrees inclination, and which for geo satellites you don't want to be dropped off there. You want to get to 0 degrees inclination, and we ultimately came up with a way to bring the satellite to a lower inclination without using up all the fuel on board, but we couldn't quite get it down to 0 degrees, and I think it was about maybe 8 degrees or something, but ultimately, we were able to end up using the satellite. At least some aspects of the satellite, the phased array worked beautifully. And one of the advantages of phased arrays were shown right there, where it allowed you to steer the beam. Satellites at GEO with a little bit of inclination make this figure 8. And when you observe them, so the phased array allowed you to sort of steer the beam so that you wouldn't lose connectivity. So that was a really good experience. Like I said, it was a great experience to be able to work with amazing people to put that satellite up.
Well, again, I think, for those that are listening, including myself, I mean, I don't think we truly appreciate or understand the sophistication or the complexity of this. The fact that you were able to salvage it, but even just the audacious nature of the mission itself, especially back then as well. And these were, very expensive, costly satellites, unlike the LEO orbit, small CubeSats that we're launching these days. You really have to do it right and have multiple duplicate, triplet, backups and fail safes and so forth. For those that are listening not familiar with active phase array, I believe it's a computer control array of antennas that creates a beam of radio waves that electronically steers to point in different directions without moving the antennas. And again, I believe to achieve high gain, these have to work at a high frequency, correct? Kind of end the radio spectrum in the UHF and the microwave bands. Is that correct?
Right. So just quite a few things there. Yeah, active phased arrays allow you to electronically steer the beam. As far as the gain of the antenna, so-called the directivity of the antenna, that just comes from any directive antenna. Dish reflectors on your roof give you a directive antenna, directive beam that points the beam towards, let's say, geostationary satellites. So if you have dish network on your roof or DirecTV on your roof, that is a directive antenna that directs the beam to point towards the geostationary orbit and a particular satellite. But as you can see, it doesn't. You don't have to adjust the satellite dish on your roof, because the geostationary orbit allows you that the satellite tracks the Earth's rotation, and it remains stationary with regards to your field of view, and that's fine. But as you go closer to Earth for low Earth orbit or other types of missions, satellites go overhead at much faster rate. They can orbit the Earth in 90 minutes. In this case, you would need either a mechanically steered antenna, which has been used many times, but they can be less reliable, or you may not be able to get as much performance out of a mechanically steered antenna, or many applications, in radar applications and other applications. A lot of this technology has moved to electronically steerable antennas, and that's what phased arrays give you. Allow you to electronically steer the beam to track the satellites. They allow you to create multiple beams to track multiple objects or track multiple satellites without having to, and it's a necessity for sort of low Earth orbit applications. As far as gain and higher frequency, going to higher frequency allows you to get higher gain, but you can get that from dish antennas as well. The thing that phased arrays give you is electronically steerable beams, as well as a lot of other cool features, like you can put the right amount of power to each beam, or you can take power that's not necessary in one beam and give it to the other one, create multiple beams, shape the beams, and do a lot of other things that traditional mechanically steered antennas or fixed antennas just cannot do.
Yeah, I mean, we're actually invested into a company that's focused on software-defined antenna in a package, and just active steer beaming that you're referring to. So we have some baseline knowledge of this. Now, phased array historically has been used quite a bit on the military context, trying to essentially detect planes and missiles and so forth. But how is it actually really kind of expanding to other applications within the LEO sats as well as drones and aircrafts?
Very good question. Yes, in fact, that's active phased arrays. Phased arrays have been around for decades and decades, many years, well over 50 years or more, in fact. And they've been used both used in radar and sensing applications, as you pointed out, for detecting moving targets, airplanes, and other flying objects, for example, or other objects. And they've been used in communications also for decades. And in this particular case, as technologies develop, we've been able to have better technologies for devices that allow you to do that beam steering and beam forming. It's called beam forming, and it's found its usage in communication satellites. In particular, as I mentioned, as we transition more from communication only from geostationary orbit or from MEO orbit into a lot of LEO constellations, as you know about, it necessitates phased arrays used for communication. So these are typically direct radiating arrays from a LEO satellite. And as you and I fly around in airplanes, we want to have connectivity. And now we're embarking on a generation of LEO constellation where it allows us to have better connectivity to our to aircraft, to drones, to future autonomous driving. Autonomous driving is going to rely on multiple sources of reliable connectivity, and one of those sources can be low Earth orbit satellites, which give you both low latency and good and high throughput. So phased array is a critical part of all of these platforms. Anything that's mobile is going to really need smart antennas, software-defined radios, steerable antennas, as you mentioned, as you pointed out, Scott.
Now, let's talk a little bit about on the ground. I know you guys focus more on in space and aerospace, but on the ground, you have things like LiDARs and cameras and, of course, radars. And LiDARs are great for kind of that immersive 3D, object classification. That's immediacy, right? But for anything that's kind of intermediate, mid-range, let's say 300 meters, whatever it is, you need radar. But historically, radars have been good in terms of identifying there's an object, but it hasn't been very good in terms of identifying what object that is. Can you talk about some of the advancement in that area? And are you guys working on that aspect as well?
We've not focused on radar applications quite yet. We will in the future. We have capabilities and people. We've been, quite honestly, as a startup, it's been overwhelming the amount of demand that's been there from all sorts of customers, from satellite customers, from direct government customers, from our commercial customers. So we've been mainly focused in communications, but we do have a couple of early programs in radar applications. Given some small changes in our technology, we've been able to use it as radar as well. But basically, electronically steerable arrays can be used for communication and radar as well. And as you pointed out, LiDAR gives you its particular advantages, and radar also gives its own advantages. And we have a few programs that I just can't quite get into in this setting, but we're starting to work in that area as well.
Completely understand. And I also want to explore, if we have time, 6G, because I think what you guys are working on is very relevant there as well. So let's talk a little bit about your core kind of product and IP around single beam downlink solutions to the multi-beam full duplex communication payloads.
You may also like our quarterly Astro Perkins event that brings some of the most notable experts and category-leading startups in their area of sustainability and human survival on Earth and in space. To register, visit astroperkins.com/events.
Right. So what we wanted to do at the onset of the company was active phased arrays are not just antennas. They consist of the antenna and the radio frequency components behind them, so-called the RF front ends. But these are low noise amplifiers and power amplifiers and beamformer chips, and many other electronics that are required to make electronically steerable antennas work. Furthermore, you also need radios and modems and compute devices, sometimes power electronics. So it's quite a bit of a stack, and hardware and software has to be combined. And so we had a goal to not only provide an active phased array, but to provide the full stack. So you can look at it as, when you buy an Apple product, you take it out of the box. It comes with everything you need. It even comes with iTunes and so on. You can sign up for iTunes. So the entire ecosystem is ready for you to be able to use your product. And in traditional sense of active phased arrays, for example, if a customer didn't have the capabilities to use our product, to use a product like this, what would they do? They would just either have to go hire people. So we wanted to create a product that our customers who are focused on their mission, let's say they have a drone company or a satellite company or anything else you can imagine, autonomous driving company. They wanted our technology, but would they have to go hire their own PhDs for antennas and RF and software-defined radio? So we wanted to create a product that would come with everything you need right out of the box, works right out of the box. It comes with hardware and software and the graphic user interface for them to use it very easily. And that's what we created. We created a full stack set of products and like a modular building block of antennas to work from various frequencies, L band all the way up to V band and so on. And then it comes with a configurable digital backend, which allows you to build quite complex payloads that go from bits to RF and gives you all the flexibility you need on a very complex payload. It could be used for a downlink, uplink. It could be used for inter-satellite link. It could be used, as I mentioned earlier, for RF sensing, radar applications, let's say, range finding, so you can determine the range between different objects. So we put our investment in creating a very software-defined set of modules and electronics that can be easily assembled by our customers, and we provide all the hardware and software required for our customers to use our products. And that's what we've done over the past 4 years. Sorry, please.
Yeah. Well, I was just going to say, from a customer experience, I mean, it's delightful to have a turnkey solution, but from the actual manufacturer's point of view, to have vertical integration across those many different layers of the RF, software defined antenna and the amplification and the chips and firmware and software. I mean, it's a lot for a small startup. So how have you guys been able to work out this portion, both from an IP and patent carve out, but also the actual manufacturing of that and the miniaturization of some of these things into usable commercial grade?
It's an excellent question. Yes, that's a challenge, right? That's the challenge is you can either focus on one product, let's say a software-defined radio, which would be certainly easier to develop with a small team. But we wanted to take this challenge on, and required a much larger investment, but also required a much larger team. To do the kind of thing we just talked about requires pretty much every field of electrical engineering and mechanical engineering and materials engineering in one place. You need at least one of each, sometimes a couple of each. And so that's what we did. We grew our team very rapidly. We went from a couple of people, 3 people. Now we're about 80 people, both in Austin and our Broomfield office. And we were able to attract a lot of talent, both in Austin and Broomfield. And we're growing the team. And we developed each one of the products, and then we integrated them all together, brought the software aspects and the firmware aspects, and did a lot of testing. Space hardware requires a lot of testing and qualification. So we've done that and worked closely with our customers. Initially, a lot of government customers give you the opportunity to try advanced technologies in some platforms. So we were very fortunate to be able to work with our government customers and prove out our technology. And now we have an opportunity to launch our own 2 satellites coming up.
Yeah, I mean, I think there's a role for SBIRs and STTRs for exactly these reasons. Yeah. Now, for some of these components, is it a combination of baseline, off the shelf with some customization modification? Or are we talking about, build from the ground up from scratch?
Yeah, so I mean, it's pretty much built from scratch as far as the design and the architecture and the PC boards, printed circuit boards are concerned. The chips, we don't design the chips. We do specify the chips, sometimes modify the chips in some way with some of our partners. But other than that, we try to utilize mostly commercial off-the-shelf chips, mostly designed for automotive parts, and then we do our own testing to make sure they meet the radiation environment for space and harsh environments. And a lot of automotive parts actually do quite well in low Earth orbit environments. We do our own testing. We use a lot of parts that NASA has had experience with, but we use basically commercially available chips, and we qualify the product around those chips. And so we design our hardware and software around them, and that we find that level of vertical integration to work for us, because then you have access to a diverse set of products across the board to provide a really advanced product, versus had we invested all of our funds towards designing our own chip, it may have not, we may have had one product, but now we have everything we wanted. Yeah. And we have kept the IP, of course, and so it's been quite successful for us.
Yeah. Just one quick comment, and then a question is, I think the product development approach that you guys are taking is so vastly different from when you were with the prime or the tier 1 previously, because it's one thing to build a satellite that is hundreds of millions, potentially even billions of dollars, versus these relatively 3-year small sat cubes that can be decommissioned easily. You don't have to harden. It doesn't, and the duplicity and all these backup. It just the level of threshold isn't just as high as before. Correct?
Yeah, exactly, Scott. That is That's quite honestly, that's something I've always, I worked all my life on those kind of satellites you mentioned that, everything is redundant. You pretty much are flying two satellites in one, sometimes, three computers for one, and pretty much everything's redundant. And that certainly has its place and exciting in its own right. But I've always been fascinated by how do you optimize for the entire system performance as a system, not as just individual components, and decentralized systems, distributed systems. I've always been interested in distributed systems. Internet is a distributed system, and when it comes to satellites, I wanted to see, from a couple of decades ago, to see low Earth orbit and smaller satellites take hold, where you have a distributed network, a number of satellites. If one of those satellites fail, you have redundancy within the plane that can replace that satellite that is now taken off, that everyone, pretty much a lot of people are doing it. And in that case, then maybe the satellites don't have to be as redundant. Maybe they don't have to be, they still have to be robust, but the entire architecture and the strategy changes, allows you to do something that
absolutely.
Exactly, right? So that makes it quite exciting, actually, how to build redundancy across the system. And it really makes it powerful, all the way down to what kind of technology, what kind of chips you can use, and what kind of performance you can provide. And I think ultimately, in many applications, not all, I'm not one to say that it has to be LEO or nothing. I think GEO and geostationary satellites have their own place, and they will for a long time. But I think it makes it quite exciting for this next generation of LEO constellations.
Agreed. Absolutely agree. Now, you have a very exciting mission coming up, I believe, in September, and depending on when this episode gets released, definitely in 2021. Your mission one, I believe, is sending hardware into space, and it's going to provide an in-orbit testbed for some of your customers to run experiments. Can you elaborate a little bit on that?
Don't forget to visit astroperkins.com to register for our next quarterly events. Past and current speakers include Damian Vaughn, former NFL player, Neil Gregory, Chief Thought Leadership Officer at the IFC World Bank, and many more. To register, visit astroperkins.com and click on Events.
Yes, indeed. We have been shipping our flight hardware actually for a number of customers, but some of these missions take a couple of years to get to orbit. And so we decided that we're going to invest in building and launching our own satellite. In this particular case, we purchased the satellite bus. These are two 6-unit CubeSats, and we purchased the bus, but we added a lot of features, added propulsion, electric propulsion to it. We added a star tracker to it, and some other features, some extra power capability, such that we could accommodate every one of our building blocks. So we could put a Ka band active phased array. We call it the Nightingale series. So we put an entire Nightingale series phased array on it, software-defined radio, single board computer, power electronics, and a bunch of other stuff. Inter-satellite link, we have an S-band inter-satellite link. It's quite capable. It can talk to another LEO satellite. And so we put a lot of capability in these two satellites and are launching them this September as a co-passenger on a Landsat 9 mission, and allows us to do our own demonstration in orbit, get our stuff in orbit and prove it. And also it allows us to provide a test bed for many of our customers. This is essentially a millimeter wave 5G terminal in orbit. So it has applications for non-terrestrial 5G capabilities as a test bed. So we've already attracted some customers, some even primes, to run some, both in government and commercial, to run some experiments. And in fact, these two missions have been sponsored and partially funded by Department of Defense's Defense Innovation Unit. They've been very kind to us, and we really appreciate our partnership with them. And in fact, we're demonstrating a couple of our IP with them, some IP that has to do with waveform switching and optimization of the link.
It's very exciting, and as I'm listening, I'm not surprised in the sense of your approach, because you're a veteran in the space. I mean, when I speak with space founders, you can always tell who are the true experts and pioneers because they really take their legacy flight seriously, and you want to get the most out of it. And I love the fact that you guys are really, truly making the most out of it for your internal purposes, but also for your customers as well. Fascinating. Let's talk a little bit about 6G again. You mentioned that this upcoming mission is going to really help with some of the testing around 5G. What is 6G, and how will a phased array system be in many ways really necessary to fully optimize or capitalize on 6G capability?
Right. I mean, I think 6G is on the roadmap, although we're still trying to really get 5G rolled out everywhere in the world. And active phased arrays are a critical part of a 5G. You need MIMO, and you need multi-input, multi-output type of antennas and steerable antennas. And 6G is just going to take it to the next level. Just more bandwidth, more throughput, faster speeds, which allows you to do a lot more, add a lot more capability, a lot more throughput. Being able to sense the environment. It goes by many different names. Telepresence, and being able to put on your virtual reality goggles and maybe have your lunch sitting on a beach or something somewhere, and be able to hear the ocean and smell the environment and have full immersion into the environment. The kind of speeds that would be require still beyond even where we're at 5G. But the core technologies are there. Better technology in more bandwidth in phased array technologies, in the network itself, in power amplifiers, in low noise amplifiers, and more efficient, better antenna technologies. All of that will come into play as it is now with 5G. So just take it to the next level. About a decade from now.
Very exciting. I mean, what a beautiful roadmap, right? Because you know exactly where you're headed and the kind of monetization from that.
Yeah.
Let's see. I wish we could, we had a little bit more time, but let me ask you one question, which is around lessons learned. So as you look at your past career at more the traditional kind of a, traditional prime or tier one to the kind of startup that you're running today, any product or project failures or just kind of lessons learned and insights that you can share with others?
Sure. I mean, that's a good question. There's always lessons learned. There's always, the thing that I've learned is I've been very lucky to work at a couple of amazing companies with amazing people, and whether it's a traditional tier one space like the company I worked for at Lockheed, or here, rigor in this kind of business is paramount. You have to have rigor in building a product, and not only for space business. Quite honestly, do any of us expect that we buy an iPhone and you take it home with all the excitement, or any other product, or you buy a car that it doesn't work? It would be very disappointing. And I grew up at a time where you could even own a new car, and there would be a possibility that it could leave you at the side of the road. It just broke. And not many of us, and I tell the younger engineers, when was the last time that you were just kind of driving and your car kind of left you on the side of the road? It doesn't happen very often anymore. Cars are more reliable. We expect our phones to work, and all of that, including the space hardware, the kind that I worked on in space satellites, and the kind requires rigor, requires systems engineering, and requires processes. And whether it's new space or low Earth orbit or this agile startup, I think what I've learned over time is that no matter how agile of a team you have and how fast you want to get a product out, you cannot lose that rigor. You have to put the rigor in, or the opportunity for failure will go up. And whether I was working on a mission to Mars or the GEO satellites, or today when we're launching our own 6G satellite, if you find that rigor wasn't applied, in designing something, analyzing something, testing as you fly. The smallest details will come back to get you, and that's the fundamental lessons I've learned over the past 30 years.
Well, I think I don't know if it's a philosophy that came from the software side only, but when you deal with integrated systems like you're doing, rigor is absolutely necessary. I'm so glad that you pointed that out. With that, I've been joined by Shey Sabripour, founder and CEO of CesiumAstro. Thank you for joining today.
Scott, it's been my pleasure. Thank you so much.
Thank you.
If you've enjoyed this episode, take a moment to rate our show on any podcast platform that you listen to. Scroll down to the bottom and push 5 stars. It's that easy. And as always, thanks for listening.